Looking more at light or electromagnetic radiation, we can see how the waves of magnetic radiation interact with each other. We call this interference. Let me highlight. So we have two types. We have constructive interference and destructive interference. And constructive interference is when waves interact so they add together into a much larger amplitude wave. So we call them in phase. And so it's like adding up two waves that are perfectly lined up. So their peaks are at the same place and their minimums are at the same place. And when we do that, the wavelength of these doesn't change. So that's still the same. But what does change is the amplitude. It's additive. And so when there's constructive interference, the amplitudes of the wave add and the wave becomes, has twice the amplitude as just one of the previous waves if they're the same amplitude. And so we call this kind of phenomenon when this is happening as being in phase. And with waves, I relate these so much to friendships. I have had lots of friendships where I'm perfectly in phase with someone and we have amazing constructive interference and we make each other better people. But I have also had lots of friendships that have quite a bit of destructive interference where our best qualities seem to cancel each other out and we kind of make each other worse for it. And that's what happens with destructive interference in terms of waves is they're out of sync or they're out of phase such that the peaks are not aligned and the minimums are not aligned either. And so what happens is the minimum value and the peak value in the waves, when you bring them together, happen at the same time. And that cancels each other out. So when we add a positive like part of the amplitude to a negative one, it'll cancel out and make zero. And so what happens is when these phases are perfectly out of phase with when these waves are perfectly out of phase with one another, destructive interference means that we see an amplitude of zero, or we just see the amplitude decrease if they're a little bit out of phase. And so destructive interference leads to this lack of wave in that place. And so this becomes useful in understanding the wave nature of light and how it behaves as a wave. And so if you have a wave go through a barrier with a slit, you're going to see a diffraction. And we see this in all types of waves, not just light, but we see this in things like waves from the ocean. So we see this kind of diffraction. And here's an example right here of a small hole in a barrier of rocks, and as a wave comes in and goes through the slit in the barrier or the opening, that wave fans out into this like half circle around it, and so the wave diffracts into this fairly specific pattern that looks like a ripple in a pond. Even, it comes out in this circular motion. Now, if instead we had a particle or a series of particles that were going through that same slit, some would be deflected by the slit and others would be, or by the barrier, and others would be able to pass through. And so we would just see particles collect in one space, whereas we would see a wave show up in a wide range that it was bigger than the actual slit or opening in the barrier. So when we look at how things behave when they go through a slit or opening in a barrier, we can see if it's acting as a wave or as a particle. And so what happens when we shine light through a slit is we see that kind of wave behavior. And the way we really test this, because otherwise we would just see kind of light on a broad range, is we use two slits because then what happens is we diffract the wave where both of those openings are, and we then set up waves that come out and they will be able to constructively interfere and destructively interfere as they overlap. So by taking that wave and creating two diffracted waves from it, we can see constructive and destructive interference, and we'll see them go kind of in alternating order. And so what we'll see is constructive interference and destructive, constructive, destructive. And we'll see a pattern in the light that shows parts of it shining and very bright. Because remember that amplitude is a measure of brightness or dimness. So when things constructively interfere and increase the amplitude, we increase the brightness of the light. And when it destructively interferes and decreases the amplitude, we see it get dimmer or disappear entirely. So we'll see dark regions that correspond with, let's do it like this, dark regions that correspond with destructive interference. And we'll see these really bright regions that correspond to constructive interference. And we'll see this really classic pattern from a double slit, like shining a light through something that has two slits in it. So that's how we test for the wave nature of light. And that might be something that's already intuitive just based on like your exposure to science classes to date. But yeah, like light is a wave. But what gets really interesting is that light also behaves as a particle. And now not in that double slit experiment necessarily. But what we see is evidence of this with the photoelectric effect. And what happens is when you shine light onto the surface of the metal, you are shining energy onto that surface of metal. And the atoms at the surface of the metal that make it up are going to absorb that energy. And below a certain threshold of energy of the light, nothing happens. You can shine it on that metal surface all day and nothing will happen. But if you get above a frequency that corresponds with higher energy, right? Remember, higher frequency means a lower wavelength, which means a higher energy. Then what we see is that the light has enough energy that suddenly an electron can be ejected. And what happens when an electron is ejected from a surface of a metal is that the atom has absorbed enough energy to separate that electron from the nucleus. We call it the binding energy. So it's absorbed, and it takes on enough of that energy from the light that the electron now has enough energy that it no longer needs to be bound to the nucleus. And so it's going to have more motion, right? It's just gonna shoop away. And so we see that above that threshold, we'll start to see electrons being ejected. And if you increase the frequency from there, we see that those electrons are then ejected with an increasing amount of kinetic energy too, if we keep upping up that frequency. But at a certain threshold frequency below it, nothing will happen. Like nothing will happen at all. And so that means that the atoms aren't just absorbing and retaining this energy. It takes a certain amount of energy to actually pop that electron off, which means that that wave of light that's hitting the surface is also acting as a particle. It has enough energy in the particle that when it collides with an electron particle, the electron absorbs that energy and is able to then take that kinetic energy and eject itself from the atom, right? And so the name for this is the photoelectric effect, and it's what's been used as evidence for the particle nature of light, that light actually behaves as both a wave and a particle at the same time. So looking at this image, I just want to point out some of our variables and abbreviations, right? We have KE is our kinetic energy. HV, this is the light shining on the surface. And where this is coming from is right here, that the energy of the photon is equal to Planck's constant, which is just a constant. So this is just a constant. Oh. Times frequency. So that energy of the photon, the particle of light, is going to be proportional to frequency. And photon is the word that we're going to use for a particle of light. And one more term that got thrown here, and we'll go into these in more detail also on the next slide, is BE, which is binding energy of the electron. And so that's that amount of energy that is holding that electron to the nucleus. So think of it as like the potential energy between those two. That's from that attractive force of two oppositely charged particles. And so, looking at this particle nature of light, this work comes from Max Planck and Albert Einstein at the turn of the 19th, 20th century. Um, is that the idea that electromagnetic radiation isn't just a wave of light, but rather now a stream of small packets of energy that behave also like waves emerges. Um, and so we call these little packets of energy, they named them a quanta of energy or photons. I like photons the best. But I could say a quanta. And so each of these photons is going to travel at the speed of light. So it will have a velocity equal to that speed of light of 3.00 times 10 to the 8th meters per second. And it will still have a frequency and behave as a wave that has a frequency associated with based on its energy. And so we could say that the energy of a photon of electromagnetic radiation is going to be proportional to its frequency, and we can develop a equation for the energy of a photon that is equal to this constant, which is Planck's constant, which is this kind of cursive H. It's 6.626 times 10 to the negative 34th joules seconds. So that's energy times time, right? And it's that times its frequency. We can then use our equation that the speed of light is equal to the wavelength times the frequency of that light, and combine these two and rearrange them to show that energy then is equal to Planck's constant times the speed of light divided by wavelength. So we can use either wavelength information or frequency information to learn about the energy of the photons that can make up that electromagnetic radiation. And so at the end of the day, light behaves as a wave, and we see that with a double slit experiment where it diffracts light and we see both constructive and destructive interference. But light also acts as a particle, as we see when light ejects electrons only at a certain frequency or above, that it can correspond to its binding energy. And so this idea of this dual nature of light leads us to be able to calculate the energy of those photons, those packets of energy that comprise electromagnetic radiation. Yeah.